Hello, everybody. My name is Sofia Corbà, and I am a PhD student at the University of Massachusetts Amherst in my last year. Today, I want to talk about my recent work on gravitational wave anisotropies in models of axion inflation. Gravitational waves have received a lot of attention over the past decade, especially after their first detection in September 2015 from the LIGO-Virgo collaboration. And the more recent evidence reported by pulsar timing array measurements of a stochastic gravitational wave background, which basically is the superposition of gravitational waves coming from a lot of different sources and directions that we are not able to detect individually. Gravitational waves can be produced either from astrophysical sources, like binary systems of black holes or neutron stars orbiting around each other, or they can have primordial origin. In that case, we call them cosmological. And in this work, we are interested in cosmological gravitational waves coming from inflation. Now, both astrophysical and cosmological sources can give rise to a stochastic gravitational wave background. So the question is, how can we distinguish between astrophysical and cosmological gravitational wave backgrounds? One possible way is to look at their anisotropies. In fact, we expect this background to show small spatial fluctuations analogous to the temperature fluctuations of the CMB, the cosmic microwave background. And in particular, we expect these anisotropies to correlate with those of the CMB if they arise from the same underlying mechanism. From this cross-correlation, encoded in this correlator here, where omega GW is the gravitational wave energy density, and zeta is the curvature perturbation related to the CMB, we can have important information about the origin of the gravitational waves. In a paper of 2024, I studied this correlator together with Lorenzo Sorbo in the model of axion inflation, and we found that it is indeed not zero, and that it can take values between 10 to the minus 4, 10 to the minus 2. Now, the observability of this result depends not only on the overall gravitational wave energy density, but also on the amplitude of the anisotropies in the gravitational wave spectra, which is encoded in this correlator of the gravitational wave energy densities. In my last paper, posted a few months ago, I studied this correlator, and I found that it can actually be relatively large, as large as 10 to the minus 1, showing that axion inflation could indeed produce observable anisotropies. So this is what I want to talk about today. I will start with a brief introduction of inflation, even if I know that many of you are already familiar with it. I will just remind you some aspects that can make it easier for you to understand the rest of the talk. And in particular, I want to talk about the scalar and tensor fluctuations produced during inflation due to the accelerated expansion of the background that we will call vacuum fluctuations. Then I will talk about axion inflation. I will highlight the parity violating nature of the system. And then I will show how in this model, we have the production of some extra fluctuations that we will call source fluctuations to distinguish them from the vacuum ones. And finally, I will present the results. According to the theory of inflation, the universe, before its standard evolution through radiation and matter era, has undergone an initial period of accelerated expansion governed by a scalar field, the inflaton, reaching in a natural way an extremely flat and homogeneous configuration. The action which describes the system is that of a scalar field minimally coupled to gravity, with a potential that needs to have a flat direction, for example, like that. Inflation terminates with a phase of reheating, where the inflaton decays into the particles of the standard model. Besides solving the rise and flatness problem, inflation provides a mechanism to explain the temperature anisotropies of the cosmic microwave background radiation, the large-scale structure of the universe we observe today, and the production of primordial gravitational waves. In particular, being the inflaton a quantum entity, it will have spatially varying fluctuations, which imply that different regions of space inflate by different amounts. And these differences in the local expansion histories lead to different local densities at the end of inflation. Very often, we are interested in the curvature perturbation related to the scalar fluctuations like this. To study the quantum fluctuations, it is convenient to do a Fourier decomposition and to study the evolution of each mode separately. And it turns out that the modes oscillate when they are deep inside the horizon, while they freeze to a constant value outside the horizon. During inflation, their wavelengths are basically stretched, and by the end of inflation, they become macroscopic with constant amplitude. And this constant amplitude will enter in the power spectrum, which takes this value outside the horizon. The analysis is pretty similar for the tensor fluctuations, which correspond to the gravitational waves inside the horizon. We start by adding spatially varying fluctuations to the metric in the form of transverse traceless tensor modes. To find the evolution of these modes, we expand the Einstein-Hilbert axion to quadratic order around Friedmann-Robertson-Walker. The resulting equation is very similar to the one we had for the scalar modes, with the difference that now we have two of them, one for each helicity. But again, the modes oscillate when they're deep inside the horizon, while they freeze to a constant value outside the horizon, and this constant value enters in the power spectrum. From now on, I will refer to these fluctuations in these power spectra as the vacuum fluctuations and the vacuum power spectra. In my work, we are interested in the model of axion inflation, in which the inflaton is a pseudo-scalar coupled to a U1 gauge field through this term here, where F is called the axion decay constant and basically determines the strength of the coupling, and with gravity through this action here. We will not make any assumption about the shape of the potential rather than it is flat enough in order to be able to support inflation. We introduce the perturbations as we did before by adding spatially varying fluctuations to the inflaton and the metric, which now assume to be an exact de Sitter plus transverse traceless tensor modes. In terms of the canonically normalized perturbations, capital Phi and capital Hij, the equations that describe the evolution of the system are these. The first for the gauge field, the other two for the fluctuations. In particular, the first equation describes the production of gauge fields due to the coupling with the inflaton. If we substitute the quantization of the field, we find the equation for the gauge field modes, where psi is a positive parameter that basically governs the amount of gauge fields produced in this mechanism. Looking at this equation, and remembering that tau is negative during inflation, we see how the positive helicity modes develop a tachyonic instability and will be therefore exponentially amplified, and they can be approximated by this expression. The negative helicity modes, on the other hand, they will just remain in their vacuum, and therefore they can be neglected from now on. So basically, in this model, only photons of a given helicity are produced, showing how the gauge modes are basically reflecting the parity-violating nature of the pseudoscalar rolling inflaton. The other two equations describe the scalar and tensor fluctuations. Their solutions are divided into two parts. The solutions of the homogeneous parts of the equations, which correspond to the usual vacuum fluctuations generated during inflation due to the accelerated expansion of the background, the ones that we called vacuum before, and the particular solutions, which correspond to the scalar and tensor fluctuations sourced by the gauge fields. To find these fluctuations, we can use the sources and the retarded propagator. As a result, the power spectra will not only be the vacuum counterparts we saw before, but they will also receive contributions from the sourced fluctuations. And in particular, due to the parity-violating nature of the system, gravitational waves with different velocities will be produced with different amplitudes. And the power spectra corresponding to different velocities will also have different amplitudes. And it turns out that for psi positive, the only contribution to the power spectrum comes from the positive velocity mode. Okay, going a little bit more into the details of how these source fluctuations are produced, we have two mechanisms. First, the background rolling inflaton, as it rolls down its potential, produces quanta of the gauge field, which in turn produce scalar and tensor fluctuations. At the same time, vacuum fluctuations of the background inflaton induce fluctuations in the family of the produced gauge fields, which are then imprinted in the source tensor modes. As a result, both scalar and tensor fluctuations can be written as a sum of vacuum plus sourced components, and the source tensor modes can be further decomposed in a part depending only on the rolling inflaton, coming from this one, and a part depending on the fluctuations, this one here. And we can calculate this part by remembering the dependence on psi, and eventually we find this expression. Okay, in the last few minutes, I will present the results. I will start with the amplitude of anisotropies in the gravitational wave spectrum, which is encoded in the correlator of the gravitational wave energy densities, normalized by the square of the fractional energy at interferometer scales. Now, remembering the form of the gravitational wave energy density and the fact that the tensor modes are decomposed in vacuum plus sourced components, this correlator will receive two contributions. The vacuum correlator, which is the result of the correlation between the vacuum tensor modes, which has already been calculated in the literature, and it turns out to be very small. And the source correlator, which is the result of the sourced tensor modes, correlation of the source tensor modes. And this is basically what we're interested in. To calculate the source correlator, we need to remember that the tensor modes are further decomposed in a part depending only on the background inflaton and a part depending on the fluctuations. And eventually we find that the 4-point function of the tensor modes can be decomposed in three contributions. One that we call intrinsic, one that we call extrinsic, and the part of the fluctuations. It turns out that all of these terms are all very small, apart from one single term, which turns out to be scale invariant in the extrinsic correlator. And this is what will give the actual contribution. Now, for the calculation of all of these terms, we need basically to compute the 8-point function of gauge fields. And I will not go into the details of the calculation, which itself, it's not very difficult, it's just very long. But I just wanted to show the form of the integral we're trying to calculate. But after some work, we find that that scale invariant contribution that basically gives the whole contribution to the correlator takes this form, where delta is a parameter that determines the running of the amplitude of the gauge field modes. And for typical values of the parameter delta, this correlator turns out to be as large as 10 to the minus 1, which is a relatively large correlation. The other correlator was the cross-correlation with the CMB anisotropies, which is encoded in the correlator between the gravitational wave energy density and the curvature perturbation, normalized by the fractional energy at interferometer scales and the amplitude of zeta. This correlator will also receive two contributions because of the fact that zeta is decomposed in vacuum plus source components. And so we will have the vacuum correlator, which is the correlation between the source gravitational waves and the vacuum curvature perturbation. And the source correlator, which is the correlation between the source gravitational waves and the source curvature perturbation. Remembering the decomposition we used before, that the tensor modes are decomposed in a part depending only on the background inflaton and a part depending on the fluctuations. It turns out that here, the important contribution comes from the vacuum correlator, and in particular from this term here, which turns out to have this form, where delta n star is the amount of foldings in which the power spectrum is approximately constant. And at this stage, for typical values of the parameters, the correlation between the gravitational wave and anisotropies and the CMB anisotropies turns out to be between 10 to the minus 4 to 10 to the minus 2. So this was all I wanted to talk about today. I will summarize the key points of this work. So this work is about gravitational wave anisotropies in the model of axion inflation, which is a particular parity-violating model of inflation, in which the inflaton couples to gauge fields. As a result of this coupling, we do not have only the vacuum fluctuations that we have in any inflationary model, but we also have source fluctuations. And in particular, the source tensor modes will contribute to the stochastic gravitational wave background. And the anisotropies will actually correlate with the CMB anisotropies with a correlation of this kind. The observability of this correlation depends on the amplitude of the anisotropies in the gravitational wave spectra, which turns out to be relatively large. These studies of gravitational wave anisotropies and cross-correlation with CMB contribute to a broader effort to characterize the stochastic gravitational wave background and to distinguish the cosmological one from its astrophysical counterpart. From the study of this cosmological gravitational wave background, we can then have important information about the physics at the time of generation of the corresponding gravitational waves. Thank you for your attention, and thanks to the organizers for the invitation.